So we left it here looking at this large boulder bar, several miles long, several hundred feet thick on the river. This is on the Snake River, by the way, and this is one of the indicators of gigantic mega floods. Now I'm going to show you a cross section of one of these backflood bars right here. And what's interesting about this is you can actually learn to kind of read how the currents sloshed in and out and back and forth by looking at the sediments they leave behind. Interesting thing about this is you'll notice there's a land surface on top, and it just so happens that this is in a place where there is an incision in the land where you could actually see, if you were walking, hiking, or riding horses or four-wheeling or whatever on top of that land surface, you would have no idea what's underneath your feet, right? But when you look at this now, this is essentially, think of this, if you look at this, you've got like where the gentleman is here, that's probably Bradley. You see down where he is, it's more fine-grained sediment. And then you look throughout there and there'll be like larger rocks suspended within. Some of those, that looks like it's probably about 3 feet in diameter. You can see it gets pretty bouldery up here. So what you have here, I've been to this spot a couple of times trying to decipher it. It's quite complicated. We went with Jerome Lessman to this site. And basically, the conclusion is what you're looking at here is multiple surges of sediment-laden water sloshing into this backflood area and sloshing out. Ultimately, where you would, to look at where the origin of this stuff was, it was almost certainly up in the Okanagan Valley in British Columbia. But the two things you would need is the lithology, which is the type of rock. And if you look in there, you'll see there's some dark rock here, which is probably basalt. And there's this light-colored rock, which I believe was limestones. And there's a mix of other things. Anyways, here's the thing. There's many, many areas of this planet where if you were able to look at what's under your feet, you would see that there's a whole epic story preserved there in the sediment layers. And one of the things, like if you look at this is probably between 12 and 14,000 years ago during the peak of the melting. I think that this was probably also deposited at the same time. I think that the waters that deposited this ultimately are what carved Moses Coulee, because this is almost directly north of Moses Coulee, and there was surges of water coming down the Okanagan Valley. And that's one of the recent papers that's just come out by Jerome Lessman, is documenting the evidence that at least some of these flows didn't come from Lake Missoula, but came from the north, which is essentially what I've been arguing for several decades now. One of the things is when I listen to some of the archaeologists, and again, Robert kind of brought this up the other day, and when I heard the debate between Graham Hancock and Flint Dibble that was on Joe Rogan, Dibble's argument boiled down to, well, you don't have any pottery. You've got to show me some pottery from that era, right? Well, here's the thing. The land that might have had pottery on it, like if you had a settlement and you've got a community of people living there and they have pottery, well, that's in that gravel pile right now. And what I would say to Dibble is this. Have you ever looked in something like this for pottery? Can you say definitively there's no broken pottery remains in that right there? No, you don't know that. Have you ever looked? Has any archaeologist ever looked? Well, no, probably not. And there are many, many, many areas where this is essentially the situation. Well, who knows? There could be all kinds of busted up pottery in this deposit. Nobody would know it. Now, this is one of the places that will be included in this tour in September. This is Oneonta Falls. Now, this is down in the Columbia Gorge, and what's interesting about this is, well, you can see the people down here for scale, and you see the undercutting. So that undercutting is the consequence of extreme turbulence. Now, the water going through here was enough to overtop the cliff that you see right here. Now, I think I've got a graphic coming up. Let's see. Well, I think I do. But basically picture this. You've got a typical valley, maybe a fairly gentle profile, sloping down to a river, right? And you've got tributary creeks that are flowing into that river, right? Now, you've got a mega flood that comes through. And that mega flood down cuts that valley and cuts a channel anywhere from a few hundred feet up to, in the case of the Columbia Gorge, there's places where it's 800 feet deep, right? Or Grand Coulee, which is 800 feet deep. So now, instead of a gentle gradient like this, you've got the uplands where it's still the original gradient, and then it comes to this place that has just been excavated hundreds of feet deep and left these shear walls. And now what happens is once the normal drainage regime is reactivated, what you've got is it flows down and then it becomes a waterfall. And that's exactly what you're seeing here. And there's, Multnomah Falls, Oneonta, La Tourelle Falls. There's a bunch of these magnificent falls along the gorge between the Columbia Plateau and Portland, right? Now, Portland, the city, is a place where the floodwaters reached a major obstruction to the west, and the waters diverged, went to the south and back flooded and filled Willamette Valley 400 feet deep, all the way to the south. Then another flow flowed to the north and went up by Astoria and then dumped out into the Pacific Ocean. Where that water turned the corner, it left a gigantic boulder bar, and that's the city of Portland is built on that boulder bar. And I've talked to builders and so forth that live in Boulder, and they've told me that, yeah, they go to excavate for a building and they constantly encounter gigantic boulders and stuff that are buried underground. Okay, so here's a digital elevation map of upper and lower Grand Coulee. Now you see where it says Coulee monocline? Okay, so a monocline, there's a cline, it has comes from the same root as the word incline, right? Now you've got an anticline, a syncline, and a monocline. And Wyatt, you can define those for me, can't you? That is an anticline. When you have compression and you have an upfold, that's an anticline. How about a syncline? When it folds down, that's a syncline. Can you remember a monocline? So you only get 66.6. Okay, yeah, a monocline, well, mono means one, right? So an anticline will be an upfold and a downfold. A syncline will be a downfold and an upfold. A monocline will just be a single fold. So that's good. Wyatt, you have earned at least, Wyatt gets an attaboy. Way to go, Wyatt. So, what we have here is the Coulee monocline. So, that monocline from the east side here to the west side here, it's about an 800 to 900 foot difference. So it's an upfold like this. Okay, so you see upper Grand Coulee, it has a lake in it. Now, that's not a natural lake, it's an artificial lake. There's a dam at the south end here this is called Banks Lake. Banks Lake Dam is here. You can't quite see it, but right up here at the top is Grand Coulee Dam. And so this is Franklin Delano Roosevelt Lake. Let's see, is it Roosevelt Lake? Maybe it's called Roosevelt. It's named after Roosevelt anyway, because Grand Coulee Dam was built during his administration in the late 1930s. And the Okanagan lobe came down along the west side of Grand Coulee, and then it arced over this way. And here you can see those lakes that were the top end of Moses Coulee that were up under the ice sheet, right? So the water that created Grand Coulee is flowing right along the edge of the lobe, right along the edge of the Okanagan lobe. Of course, again, the usual explanation is that water came from the east, from Lake Missoula. I don't agree with that. I think it came from the north, and it just basically spilled off of the ice sheet and then flowed along the margin of the Okanagan lobe. And then you can see it flows down here and it kind of is converging. You can see the monocline right here. And then it hits the monocline, right? And then it breaches the monocline. And then from that point on, you can see that lower Grand Coulee now sort of follows the axis of the monocline. And that makes sense when you think about it, because think about it. You compress the rock, it upfolds. What's going to happen to that rock? It's going to fracture and break and shatter and all of that, isn't it? In that compression and that upfolding. Well, then when the water hits that, the water is always looking to exploit areas of weakness. So right there you have lower Grand Coulee is exploiting the weakness in the rock, and that's why it follows the rock here along this string of lakes. But the water actually spread out, and one of the things that Brett's realized is that when that water first hit the monocline and spilled over, now this is about a mile right here, because if you look carefully, there's a bunch of little squares here, and each of those little squares is 1 mile. So it's about a mile to, mile and a half in width. And the waterfall itself, the water would have been 300 to 400 feet deep, and we know that because we can find high water marks along the pathway there. But then the drop-off was about 900 feet. So what you had was temporarily a mile to a mile and a half wide waterfall that was 900 feet high. So that is probably could qualify as one of the most impressive waterfalls on the planet within the last, at least few 100,000 years. The water actually spread out, so the erosion came all the way over here, and it followed this route down. At the very south end, this is Soap Lake here at the bottom of Grand Coulee, right at its mouth. And that's where the resort is that we stay at. So we make excursions, up the Coulee this way, and right in here where you have the transition between upper and lower Grand Coulee is where you have this great cataract complex that we'll zoom in on here in a second. One of the things that happened here now, once this waterfall started pouring over the monocline, what's happening, if you can picture this, you've got the rock, and then you have this difference in elevation. The water's pouring over, and it's got such force that as it pours over, it's plucking the rock. I have a picture coming up of Niagara Falls. If you've ever been to Niagara Falls, you can see that effect of the rock plucking, because at the base of Niagara Falls, there's a big pile of boulders, right? Well, now Niagara Falls is minuscule compared to this flow. So the transport capability of the flows of Niagara are not anywhere near the capacity of this. So the rocks mostly pile up at the base of the cliff and don't get washed downstream. However, here the rocks were washed out because there was such a tremendous flow of water coming through here. Then what happens is that the waterfall, as it's plucking the rocks, it's going upstream. Does that make sense? It's called a recessional cataract. So the cataract is this big horseshoe-shaped feature, and that results because of, if you think of a channel of water, it's flowing. At the bottom and sides of that channel there's friction, and that slows the water down. If you go right to the middle of the flow, that's where the water is moving the fastest. Now, the competency of water to erode is a function of its velocity. The faster it's moving, the more effectively it erodes. So if you can picture this, like picture from above, you're looking at a horseshoe shape, and the water is flowing, it's flowing faster in the middle. And then it gets progressively slower as you get to the edges of the flow. So what happens then is that the erosion of the recessional cataract is fastest in the middle and gets slower as you move towards the edges. So what happens is what's called the velocity profile of the water. Picture, you've got the water flowing, and picture like a horseshoe shape, and you've got arrows, and the arrows are longest in the middle because that's the fastest moving water, and then they get shorter towards the edges. That's called the velocity profile. The cataract will be the inverse of the velocity profile. Does that make sense? You'll see it here in a second, and we'll pull up. There's So there's Dry Falls Cataract. This is extinct, obviously. So these cliffs are about 400 feet high. We call this right here, we call this an alcove. This horseshoe-shaped feature here is an alcove. There's another alcove over here, further west. There's an alcove here. And you'll notice, okay, so this is the bottom of Banks Lake. There's that dam that I was calling out your attention to. But if you went up the floor of Upper Grand Coulee, the whole floor would look like this. Just, you can see this tremendous scouring. There's even, like, if you look right here, this round pothole-like feature, that's from vortexes, intense vortexes that are in the water. Now this water here is 400 feet deep. It's before it hits the rim of the cataract. So if you were able to witness this at the time, at the peak of the flood, you wouldn't really even see a waterfall. What you'd see is this massive river that right here would be 5 miles wide, 400 feet deep, and where the cataract is now, it would just be a bump in the river. And only at the final stages of the flood is it actually going to be a classical waterfall, like you would expect to see it at Niagara. And yeah, so here's a topographic map of the entire complex of Dry Falls Cataract Complex right here. And it's very impressive to see. And so here you can see the transition from upper to lower Grand Coulee. Here you see a part of the monocline, the uplift here. And then here's the top end of lower Grand Coulee, which is occupied by natural lakes. And then there are what are called, you know, that if you've got a river and smaller rivers or creeks are flowing into it, they're called tributaries. But if you have a flow and you have, typically this can happen during a flood and the water is flowing out of it, that's called a distributary. And this right here is the remnant of a distributary. So you got all of this water flowing down here and it splits and part of it is flowing off in an independent flow. And you can look at here, look carefully at the topography. This tortured landscape here is again what results when you have like 400 feet of water moving 50 or 60 miles an hour over bare bedrock basalt. And here you can see a cataract. This is Niagara Falls from the air. And you've got American Falls here, and you've got Horseshoe Falls here, and there's your typical, it's called Horseshoe Falls because it's your typical horseshoe shape. Now, and then in between the two, you've got this island, right? Well, both of them are recessional cataracts, but they're moving only over thousands of years. Eventually, after another 1,000 or 2,000 years, both falls will have migrated upward, and this will be like a mesa standing independent within the channel. I think the height here is about 120 feet. So once this eats its way back on both sides, they'll meet upstream above this, and it'll be an island mesa standing out within the much wider channel. Now in Upper Grand Coulee, there's Steamboat Rock, which you'll see in a second. But here you can really get a sense of this guy. Now, how many of you said you've been to Niagara? Quite a few of you. Any of you been down on the boat ride? Okay. Well, you know it's an impressive flow of water, right? Well, here is Dry Falls, again from the air. And then what I'm going to do is I'm going to juxtapose Niagara to scale so you can get a sense of comparison. So there's up in the upper left-hand corner is Horseshoe Falls at Niagara. And you're only looking at one alcove here, right? So this thing is much, much wider. It extends way over here. So you can see that it's much higher, much wider than Niagara. Niagara would be dwarfed by this complex of waterfalls here. Again, you can see Niagara, very impressive. And so here's one alcove of Dry Falls from the ground, and then we'll put Niagara in there for scale. So you can get a sense of the magnitude. This would have been one impressive waterfall to go on a honeymoon at. Although, with the caveat that you probably wouldn't survive. And what? It would be worth it. Well, so below Grand Coulee, below South Lake, you have mile after mile of this kind of stuff. This is basalt rock that was ripped out in the creation of of Grand Coulee. This is called the Ephrata Fan, and most of this is black basalt, but scattered around are these isolated blocks of pink granite, which came from north out of Canada. So this to me is an important clue that this water flow that came down Grand Coulee did not necessarily flow from the east out of Lake Missoula, but again came from the north. There you can get a sense of it. So one of the things we do, we have it, you can't see it here, but on the far side of this, there's an overlook we drive up an overlook so you can look out over this thing and you see the mouth of the Coulee, and then you see this huge fan of this material splayed out from the mouth. Now it's when you think about some of the stuff we've seen now. We've seen giant current ripples, we've seen these major backflood sedimentary sequences that form hundreds of feet of ground. We've seen the coulees, we've seen the giant boulders, we see the outwash material here now. We've seen the cataracts. So what it is, think about this, it's like when the critics attacked J. Harlan Bretz, who was originally exploring these landscapes and writing papers on it, they would take one thing and then they would try to explain that one isolated component of it by means of a more normal process, a more normal sequence of events, right? And that would satisfy them. But the thing to understand here is that when you start looking at the whole suite of features, each time you add another element to this explanation, it's like a logarithmic curve. It becomes more and more impossible to explain it by normal events. And when you look at all of it together, the recessional cataracts, the boulder bars, the giant boulders, the current ripples, all of that, there's only one other explanation. And that is you're looking at floods that are just an inconceivably huge scale. Now, I just showed you Grand Coulee. Now, Grand Coulee was one flood flow. You had Telford Scabland Tract, you had Cheney-Palouse Scabland Tract, you had the Columbia River, you had Moses Coulee. We didn't even talk about this. On the west side of the Columbia River, you have another coulee called Alta Coulee, which there's no conceivable way that could be connected to Lake Missoula over in Montana. Now, the assumption now is that each one of those had to be flowing separately. But I think there's problems with that. I think that it's almost certainly that they were all flowing simultaneous. But what that does is it jumps it up, the whole thing up an order of magnitude. Because now you're looking at, if Grand Coulee is 300 to 350 million cubic feet per second, Moses Coulee is on the same scale. So is Telford, so is Cheney-Palouse, so is the Columbia on the west, so is Alta. When you put all those together, now if they're all flowing at the same time, well, now you've got in excess of 1 billion cubic feet per second. Now we really are talking biblical scale floods here. And if anybody managed to survive, like one of the places I take people is called Steptoe Butte, which is on the eastern side of the Columbia Basalt Plateau, and it's a ancient volcanic outcrop that stood well above the floodwaters at the time. So if somebody took refuge up there and they weren't destroyed by the atmospheric phenomena that was clearly going on during these floods, when the floodwaters subsided, you would be on a prominence, and in every direction as far as the eye could see, the world would be devastated. And I don't know if we'll have time, we probably won't, but I could go on, I could show you evidence from all over the North American continent. Right here in North Carolina, I'm going to show you a couple of slides right here from North Carolina that could have only been produced by extremely large floods. And if any of you have been hiking up in some of the hollows, up in the Blue Ridge area, you're going to know that there are deposits of rocks up there, boulders that are the size, sometimes stacked up to that are the sizes of SUVs and even bigger. Those did not get those were not emplaced by the modern creek flows, okay? This is an interesting thing. Now I've taken a group here, this is on private property, so we have to get special permission, but this is back floods. And there's 39 layers here. And I'm not going to get into a big explanation because there's just too much to talk about here. But this is, think about this. Now, if I had a map, one of the things I usually like to do is I usually have my Google Maps or Google Earth open so I can jump over to a map and show you, okay, that's where this is. But picture this, you've got these flows of water coming into a basin. There's a mountain range, actually an anticline on the lower end, which in this case is the south end. There's a whole, it's called Horse Heaven Hills, it's called. It's an anticline. And it forms a rim on the southern section of the basalt plateau, and there's an opening in it called Wallula Gap. It's right near the Tri-Cities area, Kennewick. What are the two other cities? There's 3 cities right there at the mouth, right? So you had all this water converging there on this one gap. It's a mile wide and 800 to 900 feet deep. I took Graham Hancock up there when he was writing Magicians of the Gods. I took him up there because from that overlook you can see on the one direction down the Columbia Gorge where the water was going, and in the other direction you're looking out over the Pasco Basin. And the Pasco Basin is a place where all of these surging sources of water came together. Now, you have to picture that this water is choked with icebergs. It's probably ripped up entire forests. There's a huge amount of debris in it. There's more water converging onto this point that can pass through the aperture, right? Now, the water that's passing through the aperture has tremendous force to it. And somebody here went and visited the twin sisters. Who was that? Was it somebody here? Told me that they went to, there's 2 pillars right there at the mouth of this Wallula Gap that were formed by the tremendous turbulence. Also at the flanks going into it, there are huge circular potholes because the water coming in is doing this, right? What do you think happens when that water, when the volume of water flowing into that basin is greater than the water to flow out? Well, it's gonna get deeper, it's gonna backflood, isn't it? Well, what's gonna happen is that this outcrop you're seeing here is about somewhere between 600 and 700 feet above the floor of Wallula Gap. So if the water gets 600 feet deep, it's gonna backflood into this basin. And here's what I think happens, because I used to see this as a kid growing up in Minnesota in the spring when the ice would break up on the rivers. You would often have ice jams that would sometimes, if there was a constriction or a bend in the river, or let's say bridges with abutments, there would be different circumstances, but the iceberg jams could get, the broken up ice could get jammed. So what happens when the ice gets jammed and there's no flow? The water backs up behind it. Does that make sense? Well, as the water is rising behind it, it's increasing the pressure. Now, what will happen usually is that increasing pressure will push that broken ice downstream, right? And then the water flow will drop. Sometimes you will get multiple ice jams, and the difference between my interpretation and the standard model is that in the standard model, each of these layers represents an individual flood separated by 50 to 100 years from the other floods. Which means that you had there's 39 layers here. That means that you had 39 ice dams creating 39 Lake Missoulas. So then what I would say is, okay, first of all, let's take a good, hard, critical look at the whole ice dam model. And I think if you do that, you come to the conclusion that it doesn't really make sense because of the nature of glaciers. It would have to be a temperate glacier. Think of that, because, I mean, how do you have a glacier there and a huge body of water next to it, and that the only way you would have the kind of capability of holding in water would be as if the glacier was solidly frozen to the bedrock. But in a tempered glacier, you don't have that. You have water at the base of a glacier. I don't know if anybody's ever hiked over or around glaciers. You're always going to see water gushing out from the snout of the glacier, right? And if you look under the temperate glacier, there's going to be large volumes of water pooled under there. And the glacier is going to be riding on that water. Now, I think you could talk to any civil engineer and propose, here's my challenge. Here's the challenge I'm going to give to you. You've got a valley. It's at its floor, it's 5 miles wide, and at its top, it's 7 miles wide, okay? Now, what I want you to do is to come up with a dam that can dam that valley, and the water at the water level, the high water level, 4,200 feet above sea level, is going to be 2,000 feet deep. How could you do it? What material could you use? And I've actually spoken to a number of civil engineers that have had expertise in dam design, and they said, well, it's impossible. What about glacial ice? Well, as a rule, they don't know a whole lot about glaciers, but if you did talk to a glaciologist, they would probably tell you, oh, well, if it's a temperate glacier, you've got water, basal water, you've got fractures all throughout the ice, you've got water flowing through the ice, right? How in the world do you get pressures of over 900 pounds per square inch? It's an impossibility. So I don't agree that what we're looking at here represents each separate individual floods. First of all, if you have 50 to 100 years separating each of these layers, well, by the time that each successive layer is, do you think that after 50 years, that flood surface, that back flood, it's going to be mud, basically, when it's deposited. There's nothing growing on it. But if you have ever seen barren soil after a flood, or, like go to Mount St. Helens, here's a good laboratory, natural laboratory for this kind of thing. How long do you think that surface is going to be there without vegetation on it? I'll tell you how long, maybe a year. But within a couple of years, first usually you have ferns growing, and then you'll have all kinds of plants growing. Eventually you're going to have trees growing there. Think if it's been existing for 50 years. If you went out and a bulldozer bulldozed an acre of land, 100 acres of land, right, to bare dirt, and you just left it and you came back 50 years later, you think it's still going to be bare dirt? No. It's going to have grown, it's going to have been repopulated with vegetation, right? Where is the evidence that there was actually a hiatus between each of these layers? This is why I think it's more likely that what we're looking here is that you have sediment-laden back surges that are really only separated probably by a few days. That the water carrying the icebergs and the forests and everything, trying to get through Wallula Gap, jams the gap, causes the water to rise. The water rises, and in fact, early geologists in the 1800s called this evidence for big ponding of water, Lake Lewis, after Lewis and Clark. The water would rise, push the icebergs through, the water level would drop, but you're still coming from the north. Now, if you look at this, one of the things you'll notice is that the layers are bigger on the bottom and getting progressively smaller towards the top, which I believe is a function of the fact that the last one that's up there was pretty much the last of the melting of the ice sheets to the north, rather than the last breaking of an ice dam. Then one other thing I'll call your attention to before we go on here is the top. You'll notice that you've got horizontal layers until you get to the top 6 feet. And then it looks like a single massive layer, right? That is loess, and this is the stuff that was in the atmosphere. So after the last flood layer, after the last flood waters flowed off and left this top thick layer of mud, 6 feet of material precipitated out of the atmosphere. And if you recall from when Mount St. Helens erupted, you had 6 inches of ash and it turned day into night. So that's what I'm saying is that, even if you were here, you probably couldn't have seen anything. It's also said that, the oncoming flood would have caused the ground to shake and tremble from a half an hour to an hour before the flood actually arrived. Within a half an hour of its arrival, you would hear a dull roar that would get so loud that by the time it was almost ready to reach you, it would almost be deafening. So this is a lot of energy being expended here throughout this process. And this is the lower gorge, and there's a notch right up here. Look, you can see a high water mark up there, right there. Now, when that water first came through here, I don't think the floor of the valley is where it is now. I think it was above this prominence here. And so I kind of showing what I think would have been the original valley profile. And then when the water came through, this is what led. Now this picture is taken from Crown Point. This will be one of the vantage points that we visit on the September tour. And it's interesting because Crown Point is pretty much right at the high water mark. So when you stand up on Crown Point and you're looking, you can realize, okay, the water came up to this level. And again, here's a view of Burlingame Gully. Now, notice here, the rolling landscape, there's many, many square miles of this. Farmers are farming this, there are roads, there are housing developments on top of it, and nobody has any idea what's under their feet. But if you have this, what happened here was back in the 30s, they had built a big irrigation pipe to bring the water from Lake Roosevelt to distribute over the lush-covered land of the scablands for agriculture, and it busted. So there was this big gush for several weeks coming out, and it cut down this gully a couple of 100 feet deep. Well, nobody thought anything of it other than, oh man, what a disaster, we've got to fix it and all of that, which they did. But what it did was it exposed what was hiding under the surface of the ground. See, and this is the other thing, one of the takeaways from this, is that the evidence for these gigantic events is everywhere about us, but we don't have the eyes to see and understand what we're looking at. So what I do is let's start with the spectacular stuff and then progressively move to more subtle effects. And then once you understand that and can visualize and you get the eyes to see it, then you begin to see the world in a new perspective. And you begin to realize, oh my gosh, these events have left their imprints all over the planet, which they have. Yeah, so here's another close-up example of some of these. They're called rhythmites. And here, in these sandwiched, and this is 13,000-year-old Mount St. Helens ash within flood rhythmites. Now, what's interesting about that date is it's 13,000 years plus or minus like a couple of centuries. So it means that the age of that ash is right at the lower Younger Dryas boundary. Now, if the succession of deposits that created these layers is not separated by 50 or 100 years, that they were very quick with each other, it means that these floods were happening very close to the lower Younger Dryas boundary. Does that make sense? Yeah. And just a couple of quick, here's the Basin and Range Province. You actually right up here is Great Salt Lake. Here's the lower Snake River Plain. So this is in the Bonneville flood tour. We would start in this area and we would head up through this way and follow the Snake River Plain. And then I'm going to show you that all of the basins of the Basin and Range all have lake sediments on the bottom, hundreds of feet thick of these lake sediments. So I'm not necessarily, in the next graphic I'm going to show you, I'm not necessarily going to show you that I think that all of those lakes were simultaneous, but if you show water in all of the lake basins, it's this. Now this would be a very, very, very different world. And this is essentially sometime during the late Ice Age. So this is what's going on in the arid deserts of Nevada and Utah, primarily Nevada. But some of these, like this area up in here where Lake Bonneville is, I mean, that's literally so large that if you're in a boat going across it, when you're in the middle of it, you don't see a shoreline in any direction. It's like a vast inland sea. This is a product of the Bonneville flood. And this is a great example of scale invariance. You're seeing here the modern river, the Snake River. I think I've got, no I don't, but this is this modern Snake River you can see here. And this is the ancient Snake River, which is really the Bonneville flood. And the, let's see, I think it was the Bonneville flood flow was about 700 to 800 times greater than the Snake River peak discharges of floods. So again, a lot of people, from the ground, you don't really get the perspective. You've got to get up to get the big picture. And then you realize that virtually, and I can show you, but we probably don't have time, but I can show you now from what we've learned from LIDAR, is that virtually every river in North America is overfit or underfit, meaning that the river is too small for the channel it's flowing in. And it makes sense, doesn't it, that if you've got this tremendous flow, creates a big channel, once the modern river gets captured into that large channel, it's stuck. It's not, you see, that modern river is not going to flow up and flow over the rim. It's going to be confined to this much larger channel from now on until another flow of 40 million cubic feet per second comes along. And then when you're down in the floor, you come upon stuff like this. This is the sediment being carried within the floodwaters of the Bonneville flood. And you have mile after mile of this kind of stuff. And here's aerial views of desert floor in Arizona, remote desert floor, and there are fossil giant current ripples over the desert floors all over the Southwest that you don't even know from the ground. But they're there. Now their sand is blowing over them, but if you were to brush the sand off, you would have these huge dune-like remnant, basically formed of boulders and gravel from huge flows flowing over the desert floors. And so here you got what's called ribbed moraine forms, fluvial forms, or ribbed moraine forms along the Peachtree Creek, initiating Rogan or ribbed moraine. Compare with Palouse landscape. I want you to look closely at some of these features. Like, look at these are called lemniscate features. Look at this, it's almost kind of a boomerang shape, right? You see that there? And you look at these kind of undulating features here. Now this is formed fine sediment, relatively slow moving water, right? Now again, water's going to move slow if the ground is pretty flat. Well, now from the next image is from Steptoe Butte. So I'm 1,100 feet above the valley floor there, and check this out. You right, see there's that same lemniscate feature right there, that boomerang shape. It's an exact replica of what you just saw, except orders of magnitude bigger. This is an area of the Columbia Basalt Plateau where it's relatively low gradient, so the water was moving slow. So when the water is moving slow, it's just kind of rearranging the sediment, smoothing it out. It's not sculpting it. It's not washing it away. It's not flushing it out to expose the bedrock, because the water doesn't have the energy to accomplish that. Now here is, go down to New Mexico. This is the Jemez River that's next to Valles Calderas. And you can see Bradley standing on a boulder that's rounded. It's 8 feet in diameter. Now, the roundness is a measure of how far it's been transported in water. So if a boulder doesn't break apart, but it's transported in water, the first thing happens if it's fractured and got like edges and square corners is those edges and square corners get broken off and it eventually ends up rounded like you see here. Now look, if you can hike up this, we've hiked up this, miles up this river, and you find all along this river gigantic boulders. And the modern Jemez River had nothing to do with the emplacement of those boulders. They're fossil boulder deposits. And then you have colking, which is a whirlpool-like eddying current created by extremely high velocity, turbulent floodwaters that drill or can drill deep potholes along scabland channels and coulees, right? In fact, this is from the glossary of Bruce Bjornstad's book on the Trail of the Ice Age Floods, and it's a function of the vorticular motion. Think of it really like an underwater tornado. And I was able to find one graphic to kind of depict what's happening in a colking. Now, of course, in a water that's turbulent enough to cause colking, it's not going to be clear enough. You're not going to see this because that water is going to be very choked with sediment. You're not going to see this, but this shows you what's happening. Again, think of a tornado, a water tornado that can literally drill into bedrock. Now here, this is in North Carolina, Tuckasegee River. Here you have the remnant of a pothole that's 6 feet in diameter. And one thing I can absolutely guarantee you is that the modern Tuckasegee River did not create that pothole. Here's a pothole along the St. Croix River that forms the border between Minnesota and Wisconsin. Some of these potholes are up to 20 feet wide and 80 feet deep. And you see sort of remnant potholes here along the Mississinawa River in Indiana, but you can see this is called the 7 pillars. And again, what you see in here is the results of turbulence like this eating into the limestone cliffs. So once you know what to look for, again, you're going to see this all over the place. Now here is, to me, always been an interesting conundrum and it's challenged to explain rock arches like this. However, in the pathway of the Missoula floods, you find rock arches. And they were created probably within a matter of a day or two. Now, is it possible that this was created by floods? This is in Utah. How many of you ever been to Arches National? Yeah, you've seen some of these arches. Now, the thing is also, when you bear in mind that colking can also be horizontal. And what's this up here? What drilled that hole into the side of the rock there? It looked like what? An elephant? It kind of looks like, well, I was going to say yes, but what we now know is that this is giant fossilized mammoth. No, it's not. We're just kidding. But yes, I wondered about this for years, and then I finally found rock arches that were associated with both the Bonneville flood and the Missoula floods. And that's when I thought, oh my gosh, is this really possible? And then some people have asked me about Grand Canyon. If I could pull up some maps here, we would talk about that. But I will be doing this on my podcast and on my website. But if you look at Colorado Plateau, you've got the Green River, the Colorado River, the San Juan River watersheds, all of that water, and it's thousands of square miles. The one drainage off the Colorado Plateau is on the southwest rim, right where Grand Canyon is. I don't really go to the electric universe theory, and that's a big plasma arc. Because I don't need that. Because I know that you can create tremendous flows of water if you have mega precipitation events. And I think when we go back and we look at this, okay, there's no glaciers in North Carolina, right? I've got other images where I can show you. I've hiked all over the creek hollows of North Carolina, of Tennessee, of Virginia, and you'll find the same thing, all up and down the whole spine, all the way up into Pennsylvania. You can follow it all the way up to the rim of the ice sheet up there. And this was not being fed by direct glacial water, so where did this water come from? Well, it had to have come from intense, prolonged rainfalls. So now here we could say, well, perhaps we could conjecture that the sun would be able to evaporate enough water and inject enough water into the atmosphere to cause extended rainouts, but obviously so could impacts. And if you had impacts into the oceans or impacts into an ice sheet, if you have a hypervelocity impact into an ice sheet, I showed you even a Tunguska-sized object could release energy on the equivalent of 15 megatons. I mean, what if you had dozens or even hundreds, or possibly even more? What if you had something along the line of Shoemaker-Levy 9 even? I always have thought now since 1994, maybe nature was giving us a little clue as to the nature of what happened at the Younger Dryas, that it might have been an event similar to, but on a smaller scale, of course, than Shoemaker-Levy 9. And we're not going to get into this today, but one of the things that I've done is following in the work of John Shaw. I do believe that he was right, that drumlins are elongated, fluviodynamic or aerodynamically shaped hills that were produced by extremely intense subglacial floods. See, so you have water flowing under a glacier, and the glacier forms a lid, which then forces the water to flow under greater pressure than if it was flowing under a free surface, where it could go to any elevation it wanted, right? But with that ice cap over it, it's forced to flow under pressure. And what it does is, picture this: you've got the land, the glacier grinding over the land, pulverizing the land, forming the till. Remember, the till is the material that composes moraine. Then you have the high pressure subglacial floods that now shape that till into these aerodynamic forms. And I'm going to show you a couple of drumlin images in a second. So now we can add potholes to our list of diagnostics which are consistent with gigantic water flows. Natural bridge of sandstone in Kentucky. And again, how do you explain this? When we actually look at things like this and this, they are not being produced by modern processes. They're being slowly destroyed by modern processes. They're not being created. This thing here is a fossil feature. This is a fossil feature. These are not being created now. Show me anywhere in the world today where something like this is being created. Good luck. But they are being destroyed. So I maintain that features like this cannot be explained by resorting only to processes and forces like we see going on today, because we don't see it. So if that's true, then they're created by forces and processes that are no longer operational. Boulder fields, another example of a diagnostic. This is in Pennsylvania. We could talk about this a lot, but this is what happens when you have a slurry moving out over a relatively flat piece of ground, and then the finer grained matrix that these boulders are being carried in gets eventually washed away, leaving only the boulders. This is here the Tuckasegee River, and it has numerous potholes, and you see, the way to understand what you're looking at here is that this is literally the wreckage of the previous world. If you want to use more prosaic terms, this is the wreckage of the antediluvian world right here. That's what you're looking at. The modern flow, you can see the modern creek flowing right down here. Do you think this creek emplaced these boulders? No. Well, you could say, well, there's big floods along there. Yeah, sometimes there might be a big flood that lasts a day or two. And you can go up there. I've gone up there after, there have been large major storms, floods today. The boulders are still there. They haven't been moved. Some of the smaller ones may have been moved a few feet, but not things like this. No, I mean, this is a pile of gigantic boulders. Now, how do you explain getting that there? Well, you do not get there by gradualistic processes. This is along the Cumberland River in Kentucky. Look at the size of those boulders going up into the trees. Do you think the modern river put those boulders there? No, they didn't. And in fact, just upstream from these boulders is Cumberland Falls, which is a recessional cataract. So now you have the association of giant boulders with a recessional cataract, and on the upper rim of that recessional cataract, you have extremely scoured rock, just like I showed you above the rim of Dry Falls Cataract, which again is the sheer force of the water moving over the rock. Along the Wabash River in Indiana, you've got very similar to what I just showed you. You've got giant backwash features there. Look again at the top. The vertical stuff, that's the loess. That's the stuff that came after the flooding was over. This is the stuff that came out of the atmosphere. And I think the only way to explain it is that it was a rainstorm of mud. And you can look in, if you look up loess, L-O-E-S-S, you'll find some interesting stuff about it. But you'll also find that it's controversial as to how it originated, right? So again, here you have gigantic floods, and then look on top. So you've got under your feet, you've got these giant flood deposits. Then you've got this loess, which I attribute to a rain of mud. And then on top of that, you've got the modern world. The farms, the houses, the forests, the trees, the meadows, et cetera, et cetera. But then what's underneath your feet? What's underneath your feet is the remnants of the antediluvian world. Now, what I'm showing you here in North America, we could go all over the earth and find the equivalent. You see, Okotoks, the big rock, Alberta, Canada. This is an 18,000-ton behemoth sitting on the plains or the prairies of Alberta. Now, what's interesting about this rock is that it had to have been transported by icebergs. It's transported nearly 500 miles from its place of origin up on Mount Edith Cavell, which is up in Jasper. It's a type of metaquartzite that's only known to exist on Mount Robson and Mount Edith Cavell, which are up in Jasper Park. And here it is sitting out on the western prairies of Alberta, south of Calgary. 18,000-ton metaquartzite boulder that's now broken into 3 pieces, and you can actually see that how it's sunk. It's actually, as it sunk, the 2 pieces split apart. Now also notice the sharp edges, right? You're not going to transport that rock 500 miles within a glacier and then have it come out that pristine with those sharp angles and corners like those. Those would be ground off completely, or the rock would be pulverized. The only way you're going to get this rock that's in 3 pieces transported hundreds of miles from its location is via iceberg transport. Now, what's interesting about this is, again, we're talking about an iceberg that's the size of a tanker ship. So think about the scale of the water flows that would be transporting that. Now, what's interesting about this is that the Missoula flood stuff that I've been showing you is on the west side of the Continental Divide. This is on the east side of the Continental Divide. The source rock, the metaquartzite source rock, is on the west side of the Continental Divide. So now we have a very interesting problem here. We have to quarry this rock. Boulders, and this is only one of this is the largest, but it's a train of boulders called the Foothills Erratics Train that's over 500 miles long. It comes from where the Athabasca River discharges out of the Rocky Mountains, north of here, turns south for 500 miles and ends in Montana, right? How do you do that? How do you get an 18,000, we're using this, how do you get an 18,000-ton boulder quarried from the shoulder of a mountain, put on a chunk of ice that's now being floated, a chunk of ice the size of a tanker ship, set into a flow of water that can float an iceberg that far, transport it hundreds of miles and dump it out on the prairie? How do you do that? Well, it's a very interesting sequence of events by which such a phenomena could occur. First of all, you have to have something powerful enough to break off gigantic chunks of rock, literally from the flanks and shoulders of these mountains. At the same time, you have to be fracturing the mountain glaciers that are filling these valleys and in areas, because at the time now, bear in mind, these huge mountain peaks are only the peaks of the mountains are sticking above the ice, right? So now you have to shatter those mountain peaks, load up the glaciers, fracture the glaciers, melt the glaciers, so you've got the meltwater to carry the icebergs that were formed out of the destroyed glaciers, and then that has to float to the south. And then as you get down to the near the Montana border, here's an aerial view of what you're seeing. There's a little white line right here These are gigantic current ripples. That line there is nearly a mile long. So you can see the scale of these current ripples. And where is all this water going? It's created a gigantic carved valley that is now the valley occupied by the Missouri River. Okay, are you starting to get it here? Are you starting to get this picture? We are living literally in the ruin and wreckage of the former world that preceded us here. We're living on top of it. The gravels that we have used, the limestones that we've quarried, and the gravels we've used to cast the concrete that we've used to build our civilizations are literally the remnant of that former world. We have built our new civilization out of the wreckage of the former antediluvian world, and this is a simple scientific fact. How many people realize this and understand this? Almost no one. But it is a fact, and it's a demonstrable fact. And we could go on and on and on and on. But I think we've managed to get to the point. I think we'll end this session by introducing you to drumlins, because drumlins are a very important key, and I think drumlins are going to be the key to understanding where those sources of energy occurred on the ice sheet that we could then blame on the melting, the catastrophic melting. This is a drumlin. Blunt end faces up current, tapered end faces down current. Drumlin swarms. Drumlin swarms. Giant current ripples. These are up on the Bruce Peninsula along the shore of Lake Huron. We see giant current ripples. Here's what happens. We see a drumlin swarm under where the ice was, showing that there were water. Now, how do we can demonstrate that it almost certainly that those drumlins were created by gigantic subglacial floods is because where that water emerges from the source, the edge of the glacier, we find giant current ripples. So this transition from water flowing under pressure to now water on a free surface. Is that making sense? I hope so. Gigantic ripple forms in western Nebraska. Here's a forest-covered drumlin in Saskatchewan, buried under thousands of feet of ice, but you had gigantic flows, in some cases flows that would have been several hundred miles wide of water subglacially. Now, so here's the problem. See, and this is why John Shaw's work was always rejected, because just like with J. Harlan Brett's, when he first proposed these gigantic floods, all of his critics said, well, you can't provide a source for these floods, therefore they didn't happen. And he said, well, I'm not sure where, he speculated. He said, I'm not sure where the source of the water was, but the floods happened. I mean, the evidence is conclusive. It's incontrovertible. These floods happened. Right, now eventually when it was proposed that Lake Missoula was the source, it was almost like all of the geologists that were desperately trying to find some modern analog went, oh, okay. Well, it's just we know that we have ice-dammed lakes. We've seen them. They're in Iceland. We know in Alaska and British Columbia. We've seen them in Scandinavia, et cetera, et cetera. So all we have to do is just extrapolate upwards, no problem. End of controversy. The floods happened. It was just a big ice-dammed lake. End of controversy. That's pretty much where it stands today, right? The problem was, though, that there's so many inconsistencies within that. And now we come fast forward to the 80s and the 90s and the work of John Shaw, and he's proposing drumlins were formed by subglacial floods. And the critics all said, well, some of those floods you're proposing are huge, like the Livingstone Lake event that you've talked about, and you're saying 84,000 cubic kilometers of water total were involved in that? Get out of here. Can you provide a source for that? Well, I'm not sure. Could it be subglacial? Well, no. There's no way that you could form a water reservoir that big under the ice. What about on top of the ice? Supraglacial. Well, same way, because we know that every year glaciers will get meltwater on the surface because of the warm weather of the sun, and then eventually that water will drain through the glaciers down to the bottom, and it'll flow out, but it doesn't produce drumlins. So the critics said, if you can't provide a source for this water, those drumlins are not produced by subglacial floods. And he couldn't. He passed away before he could, but we had communicated with him just before this was about a year, 2 years before COVID hit. We were going to go and visit a place up in Canada called Lake Nipigon. Look it up, Lake Nipigon. Look at the maps carefully. And he was going to go with us. And then 3 weeks before we were to depart, he passed away. So we did not do that trip. So that's still another upcoming trip in the future. But the critics said, there's no way you could produce a reservoir that will accumulate 84,000 cubic kilometers of water to create these vast drumlin swarms. Here's what I would tell you to do. Go to Google Maps and go to terrain view, right? Then, here's a good start. Go to and explore the area between the Finger Lakes of Western New York and Lake Ontario and see what happens. Zoom in on that region when you're in terrain view, the 3D view, and see what you see. Now, they said to Shah, if you can't provide a source for the water that creates these subglacial floods, then it was not subglacial floods, so get out of here. And he couldn't. However, if we have a scenario, one of two. Now, my preferred scenario is multiple impacts into the ice sheet. We don't need a reservoir. We have instantaneous melting. We have instantaneous fracturing of the ice, which now allows easy access to the base of the ice by all of the superglacial melting that has occurred. We also have injection of water vapor on a large scale into the atmosphere that's going to require a rainout. And I think from having studied the erosional forms of where the ice sheet was, the drumlin fields, I think I can pinpoint at least 7 areas where there were actual impacts into the ice sheet. Now, using Robert's scenario, it would probably be solar plasma bolts or something that would produce the same thing. I'm going to come down on the side of impacts. I am not going to eliminate or reject out of hand Robert's ideas. I think we need to look at all of the evidence, but I think we can pinpoint, and I just gave you a hint. Look at Lake Nipigon. Also look at Lake Saint Jean in Quebec, and look at Great Bear Lake in Northwest Territories. So do some research on your own. I think you'll have fun with it. So aerial view of Livingstone Lake drumlin field, and we'll end with this. Here you can see gigantic meltwater flows coming south. And this is Lake Winnipeg up here. There's Lake Superior. You can see very clearly the flow paths, can't you? Look at the size of those flow paths compared to Lake Superior. They're huge. These are gigantic meltwater flows coming off the Laurentide ice sheet. And then look up here. You can see the streaking, the flow here. You had water flows coming down this way. You had water flows coming this way. So do some research on your own. You can start with Google Earth, great tool. The National Map Viewer. It's put up a U.S. Geological Survey, and it's based on LIDAR. You'll have fun with it, and you can contribute to this research, and you'll make discoveries. So I think you've got a perspective. I hope I've warped your minds a little bit. And ultimately, of course, what I'm trying to do here is connect these kinds of events, the things that have done these kinds of things and left these kinds of impressions on our planet with what's going on out there, connecting earth and sky. And I think we could have a potential explanation why our ancestors were so obsessed with tracking the motions of the heavens, for multiple reasons, but that would be one of the most important. Okay, here's 2 quotes, and then we'll end with that. Sir James Hall, one of the founders of geology back in 1815, in a paper titled On the Revolutions of the Earth's Surface, from the Transactions of the Royal Society of Edinburgh. The facts brought forward in the following paper, according to my view of the subject, clearly indicate the operation of immense torrents. And he's talking about over Europe, right? Now let's fast forward to two of the most prominent paleohydrologists in the field working today, one American, one Russian, Clute, Baker, and Kamutsu. So, wait a minute, there it is, yes. From 1999. Recently identified Pleistocene flood features in the Eurasian continent indicate that planetary scale movement of water has been a major agent in shaping the landscape of our planet. Let that sink in. Planetary scale movement of water. Now, when people like Flint Dibble and some of these archaeologists and stuff are dismissive of, oh, well, that was just a local flood. No, dude, you got no clue. You got no clue. So don't be so damn dismissive and arrogant because you don't know what's going on here. You have no idea why, because here's the thing. The kinds of things I have shown you here today and yesterday, if those kinds of events were to happen again, if we were to have a planetary scale movement of water, 10,000 or 15 or 20,000 years from now, what would archaeologists find to demonstrate that we were here? Not much. Not much. So on that note, I think we'll conclude for now. Just by the way, here's what visualizing a flow of what 300 million cubic feet per second might look like. And this is from Albert Churchward's book on Atlantis. So he was kind of already onto the thing. And we'll stop there. So thank you guys for coming. And to me, it's been a great weekend. I'm really hoping some of you guys really get into this kind of research. And if you make some good discoveries, let me know. It's a big task. There's a lot to learn here, and there's a lot of things. What we've looked at is only a small piece of the puzzle. So there's a lot more to learn, and there's a lot more for contributions that can be made by people who aren't quote-unquote professionals. Okay? All right. Thanks again.